Hello, Physics 30s. It's Mr. Jukely here. Today we're going to talk about Unit 3, Lesson 4, Electromagnetism Rules, Hand Rules 1 and 2. So if you're not already there, please open up your booklets to that Lesson 4. It's on page Lesson 4. It's on page 111 of our workbooks. So just looking at these two photos that we've got right off the bat here, you might think to yourself, oh, that's nice, Mr. Jukely's giving me a thumbs up because I'm an awesome physics student. Well, that's true. You are an awesome physics student, and you do deserve a thumbs up. This is a little bit more than that. This is the shape that we need to make for both Hand Rule 1 and Hand Rule 2 as we go through. So just take a moment and get out your hands. I always just kind of describe this as almost like Lego hands. If you could almost make Lego hands. So you've got your thumb pointing upwards. This is going to just destroy this. And then you've got your fingers kind of curled around, but you're leaving a bit of a hollow space in there, right? And that hollow space, let me clean this up a little bit, is where we're going to fit either wires or solenoids. And we'll talk about exactly what we mean by wires and solenoids in a bit. But a wire is easy to describe. So a wire might be coming up here and then finishing up there, and it'll be carrying current, right? So it's as if your hand is wrapping around that wire. This one's a little bit harder to draw, so this wire's got to be going down, I'm a terrible drawer, into the page, and again, you are wrapping your hand around that wire. One of the issues that we'll see here is actually drawing a 3D image on a 2D page. That's the issue, entire issue that I've had here. So we'll look at a couple little conventions that we use for that as we go through as well. So yeah, and one of the things I guess we're going to look at today and really start to look at is this is EMAG, or electromagnetism. So we're looking at the relationship between electricity and magnetism. So we've already seen, and I bet you anything in the last lesson you started to notice some similarities between electricity and magnetism. So some of the similarities you may have noticed are there's two possible natures. So charges, we could have positives or negatives, whereas magnetics, they form dipoles. We could have north or south. Awesome. They both act at a distance. So we know that like charges repel and at a distance. So with this kid's hair, it's sticking out all wild. I've never seen a Van de Graaff work this well. I would love to get one that goes that well. But we see it all standing out. So all of this kid's hair has, say, positive charges, and positives don't like being next to positives, so they repel each other, and then they stand out like crazy. Here's a whole bunch of magnets that are all stacked up, and on each magnet, I'm just going to use the top one as an example, we've got a force of gravity pulling it downwards, and we've got a magnetic force, Fm, pushing it upwards. That magnetic force has to be coming from a separate magnet. So each of these are there. And then we could guess maybe this one's north and the top side of that one is north as well. Hopefully you can see that marker okay. And they would be repelling each other from a distance. So another similarity that we've seen is that their electric fields even look similar. So when I'm checking out electric fields, so this is between 2-point charges. I've got a positive charge that's making things worse. Let me get rid of that. A positive charge on the left-hand side and a negative charge on the right-hand side, and we see the electric field is the direction a positive would want to go if it's there, or if we had a positive test charge. So it's away from positive and towards negative, so we can see each of those away from positive and towards negative. The magnetic field looks very, very, very similar, so we've got a north on the left and a south on the right. And again, it's where a north test particle would want to go, or where the north pole of a compass would point, and that is away from north and towards south. So these are two examples where we've got opposite things coming in, but even around similar things, it's always going to look the same. So positive and negative, or positive, positive, negative, negative, and then same thing, north, north, south, south. The field lines are going to look essentially the same. Then we've got, so this is one thing that I didn't show you in the last one. So here's a magnet, and around this magnet are a bunch of iron filings. Iron filings are just like little tiny particles of iron. Typically, if I were to shake out a bunch of iron filings, they'd all be scattered. But around a bar magnet, it actually shows us the field lines, which is really neat. So if we were to trace some of these, so I'm working on the right-hand side of the magnet here, if I were to trace some of these lines that the that the iron filings are making, they actually start to make and start to show us our magnetic field lines, which is really cool. So it's a really easy way to show magnetic field lines is just to sprinkle those iron filings, those little almost like powdered iron around a magnet, and we can see the field lines. So last similarity that we look at here is they both cause induction, and they can both attract things that are seemingly not magnetic or seemingly not electric. So the example that we looked at in class was we had a ebonite rod attracting little bits of paper, and they could attract them from a distance. The ebonite rod was charged. This is a glass rod, by the way, but the ebonite rod was charged. The paper was neutral, but it was still able to attract it. Same thing with magnets. They can induce a magnetic field in paper clips or change those domains inside of the paper clips to create an actual magnet out of the paper clips. So the paper clips themselves, while they're sitting there, domains are kind of scattered, they're all over the place, but in the magnetic field of the big red magnet there, they would all align themselves and become magnets themselves and then be attracted to the bigger magnet. So lots and lots and lots of similarities. In 1820, there was a guy named Hans Christian Ørsted who really started to put this together and really started to see this. So I'm going to leave a couple links in our Google Classroom there to check out a couple of YouTube videos if you want. Realistically, you could just search magnetic field. Yeah, actually, this is probably easier. Magnetic field around wire. And you'll see a handful of people trying to explain this. I would look for videos that have like real life pictures rather than hands and stuff. We're going to be drawing, like attempting to draw things in this class. But yeah, if you can actually like search a couple of videos, again, I'll try and post them on our Google Classroom here to see how this actually works. But yeah, so he accidentally discovered, apparently the story goes he was teaching a lecture and discovered the relationship between electricity and magnetism. So he had a wire set up, a current carrying wire set up, and he essentially, so I'll show electrons are flowing through that, and had a compass and saw that that compass needle was, this is a terrible drawing, was deflected because of the current carrying wire. So just to show a little bit nicer piece with this, the top ones, we've got iron filings, and iron filings around a wire that is not carrying current. Oh, and by the way, I is current in physics. So it's our variable for current. So from here on in, I'll probably using I, but carrying, spelling things wrong. How embarrassing. So anyways, I've got that wire, and both of them on the left-hand side are not carrying any current, and you'll see that the iron filings are kind of scattered. They're just kind of a powder that's sitting there. There's a whole bunch of compasses on the bottom one. The compasses are pointing towards our geographic North Pole or magnetic South Pole, so you can see they're all kind of lined up this way ish. Again, that's for not carrying current. And then on the other side over here, we've got wires that are actually carrying current. And what I mean by carrying current is they're carrying electricity through them. So with the top one, the iron filings, remember the iron filings always line up with the magnetic field, and we can see the iron filings are lining up in like almost perfect circles around that wire. And then the other thing on the bottom, we look at this, we know that the compass needle will point in the direction of the magnetic field, and if we look at how each of these are pointing now, they're pointing essentially in a circle around that current carrying wire. So long story short, with both of these little experiments that people have done, and Hans Christian Ørsted has started off, we figured out the direction of the magnetic field around a current carrying wire. So a current carrying wire first can make an electric field, so it has to have electricity going through it. And then second, we now know the direction. So the easy shortcut that we've got with this is essentially making that curled hand shape, and it can help us tell the direction of the magnetic field around. So what we've got, and this is called hand rule number 1, abbreviated as hand rule 1, and in particular, for negative charges, we want to be using our left hand. For actual electricity, it is negative charges that are moving around. The positives are kind of locked into place inside of the nucleus. You may here and there talk about conventional current. Way back when people didn't really understand electricity, they looked at positives moving around. Not really the case. But for negative charges, which is what is actually happening inside of wires, make sure you're using your left hand. So in particular, we can call this a left hand rule number 1. So with any hand rule number 1, essentially we got our thumb is the direction of the current through the wire, and our curled fingers are the direction of the magnetic field. So as I go through and as I look at this little example down here, so I've got a wire that is carrying current from negative to positive. That's pretty standard. So the electrons are flowing upwards from negative to positive. I've got a picture of my left hand, and I know I'm looking at those electrons, so I know I'm going to be using my left hand. And I need to orient my hand, so I need to change that so that if the electrons are flowing upwards, my thumb is also my thumb is also pointing upwards. So I need to take my hand and kind of align it or picture myself holding that wire. So I can picture myself holding that wire. It's coming up there and the electrons are flowing up through that wire kind of like that. So align your hand with the page. Pretend you're wrapping your hand around that wire. If it helps, have a pencil to wrap your hand around. Pretend that's the wire. And then the electrons are flowing upwards on our page. So that means that the thumb needs to be pointed upwards. Now our curled fingers, I like to really focus on my fingernails for this. Whatever direction my fingernails are in is the direction that the field is pointing at that particular space. So if I look at my fingernails on this picture in the front, I'm going to highlight my fingernails, give myself some nail polish. With blue, my fingernails and the tips of my fingers are all pointing, won't be able to see that at all, are all pointing in this direction. So across the very, very front, the magnetic field is going in this direction. Hopefully you can see me highlighting and drawing the arrow there. But then if I just rotate my hand a little bit and I'm thinking, okay, well, if this direction my fingers are, if I look at this little space out here by my knuckles, realistically, that's coming out of the page. We need a convention for this to show that it's coming out of the page. So the convention is whenever we're talking about out of the page, so vertically out of the page and towards you, we're going to use a circle with a little dot, or sometimes you just see a whole bunch of little dots. If it's ever going into the page, so we wrap our fingers around, and it turns out on the other side of the wire, it's going into the page. Our fingernails would be pointing into the page. We'd use a little X. One easy way to kind of remember this is to pretend you are in archery. So if you are the person who is shooting the arrow, you're essentially going to see the fletching or the feathers on the arrow going away from you like that. If you are being shot at from an arrow, you're going to see the point coming towards you. So away or into the page and out of or towards you are the two conventions that we need to know. So hopefully this is making sense for people. It's kind of hard to show. I am not a video expert, so this is probably the best I've got. If you're having a really hard time understanding, I would check out again a couple of YouTube videos. Just look up hand rule number 1 or magnetism hand rule number 1, and there's definitely people who are better at videos that can show you. So yeah, other things, and we kind of already mentioned this one, if we are ever looking at positive charges, so positive charges don't really flow, so instead what we're looking at is we've got a proton that's moving through space. So in this case, our thumb is going to be the velocity of the proton moving through space, and our curled fingers are still going to be the direction of the magnetic field around it. So you can kind of see already what we've got, the diagram right here. So the proton is moving upwards. Proton, just highlighted, I guess, this way. Proton is moving upwards here. So if I were to wrap my hand around that path of the proton, or the path of the velocity of the proton, my magnetic field would be my curled fingers, and you can see they're curled around this direction. So magnetic field flows around in that direction. So I would take my hand I would rotate my hand so it matches the picture. And notice in this case, I have got my right hand. There's no watch on this, so that's how you know it's my right hand. But I would take that, I would line it up nicely so that I'm essentially pretending that the path of that proton is going straight upwards. So my thumb matches the path or the velocity, and then my curled fingers are wrapped around it. Cool. So your turn to try it out here. Sketch the field around this wire. So remember that electrons are moving from the negative to the positive, so I'll help you out with that one. Electrons are moving this direction. And then for part B, what is the direction of the magnetic field at point A? Now don't get confused, point A, that is just a dot, just a random point in space. It is not saying that it is out of the page. Your job is to determine whether it is into, out of the page, left, right, up, down, all those different things. The dot is just representing the point. So put your video on pause right now. See if you can line your hand up so that you can figure out which direction the magnetic field is around the wire, and see if you can sketch it using our conventions, and also figure out the direction of the magnetic field at point A. So again, put video on pause and try and figure that one out. So hopefully you've had the opportunity. So I'm going to grab my hand right here. I am going to rotate it so that my thumb is matching the direction of the current. So the current is going towards the right. My thumb needs to be pointing towards the right. And then I'm going to pretend with this that I am hanging on to that wire. So the wire is going through my hand, and I'm kind of holding it in my palm. And then I can see with this that the magnetic field, well, if I look at the bottom, it's coming out of the page. So I'm going to sketch that coming out of the page. If I rotate my hand just a little bit, we would see that it is going into the page up top. And then realistically, like this might be a little bit harder to sketch. So there's our convention into and out of the page. But realistically, I'm kind of coming out of the page here and then back into the page there. It would also be up across the front because our fingernails are pointing up across the front. Perfect. So that is A. For B, similar sort of idea, except now I've got my right hand. Whoops. There we go. I've got my right hand out. So I'm going to line my right hand up so that it's in the same direction, or my thumb is in the same direction as the velocity of this proton. I know it's my right hand because it is indeed a proton. So it's going to be going downwards. And then I think, let's see, where's an easy place to put this? That might be below, I suppose. So I've got the proton that is now moving downwards through my hand. And if I follow my fingers around and I kind of wrap my hand around, I'll see that it's coming out of the page over here and into the page over on this side of the wire, and then across the front. So again, this is our magnetic field. And over here, I guess I should mention that as well, our magnetic field that we're sketching in purple right now. So again, hopefully this makes sense. Now, one thing that you might be asked to do is to show your work for this one. So showing your work, we already know, let me just, whoops, hold on. We already know that we are going into the page and out of the page for this one, but if we wanted to show our work, and so this is how I know, all we'd really need to do is say, okay, well, which hand rule am I using? So we're talking about electrons flowing. So we're using left hand because left hand is for negatives. And we're looking at the magnetic field around a wire. So all we really need to do is say, okay, well, our thumb is the electron flow or the current. And our curled fingers are the magnetic field. So B. That's all we need to do to show our work. Same thing with the proton. So again, just let me get out my right hand. We said that it was going into the page on this side and out of the page on that side. And because it's a proton, I would now be using my right hand. It's still rule number 1. So my thumb is now the velocity and my curled fingers are the magnetic field. Nice. So that's not so bad. Not so bad at all. Next thing that we want to talk about here, so getting into hand rule number 2, is, well, one current carrying wire, the magnetic field is pretty weak typically. But if we have a whole bunch of wires together, we can make a significantly stronger magnetic field. So the tool that we use to do this is called a solenoid, and I always argue with the class. I get out, it's not so much an argument, I guess I argue for this, but I would say that the solenoid is probably one of the most important inventions of like humans' modern history here. It is big, 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 because anything electric, well, most things electric, I guess I should say, deal with solenoids in some way, shape, or form. Just about everything electric. And think about all the electric things that you're using, even right now. In your house, right? Like it's a big part of our lives, and a lot of them are based on solenoids. So if you want more information on that, just look it up, and we'll be going through a couple things like electric motors and generators and stuff like that. Even those two things are huge. The electric generators is the #1 way that we generate electricity right now, and then the motors, this is anything that's electric and moving has a solenoid that helps with its motor. But anyways, I won't ramble about that too much. Solenoids are really, really important. Essentially what a solenoid is a wrap of wires that are all wrapped exactly the same way so that electrons all flow exactly the same way. So if this was my negative side and this was my positive side, the electrons are flowing up, they're going around the back, they're going out the top, and then they're going down the front and then into the page in the back for this one. And they are flowing the same direction every single where you look, every single place you look. So one mistake that people kind of make with these is they say, yeah, electrons are going from the negative to the positive. That's not the mistake. That's true. They are going from the negative side to the positive side. But the fact that they're going this way through the solenoid doesn't matter even a little bit. Right, so I'm even going to get rid of that. What's more important is how the solenoid is wrapped and how they're moving, you know, out of the page or down across the front or any of those pieces. So it's actually more important how they're moving in the circular pattern around the solenoid itself. So again, key sort of idea is the current goes in the same direction for each wire, and this creates a much, much, much stronger field. So that's what we're looking at for the next little bit. So consider this solenoid, right? And consider little pieces of this. Can you use and pretend that we've got left hand rule #1? Well, not really pretend, but pretend that we're just dealing with one wire coming out of the page at the top. So just deal with this one little section right here. Can you take a moment, put this on pause, and see if you can figure out the direction of the field around that one section of wire coming out of the page? Go ahead, put it on pause, try it out. So what I'd look at for this is if I'm trying to figure this out, I need a little bit of a different view for my thing. So I took pictures. I just took a bunch of pictures of my hand here. Why can't I move this? There we go. And if I'm thinking about that one wire on top, now I need to orient my hand so that my thumb, you can see the tip of my thumb right. Let's get back to thing I can draw with. The tip of my thumb is right there. So my thumb is now coming directly out of the page, and my curled fingers are wrapped around in this direction. So anywhere you look, it's wrapped around in that direction. Now, if we expand this a little bit, well, actually, first let's look at the bottom one. Let's check out the bottom one as well. So if I were to grab a different view of my left hand again, remember, you can always tell it's my left hand because I'm wearing my watch on that hand. Now, in this case, notice that my thumb is pointing into the page. So there's the tip of my thumb pointing directly into the page, and my curled fingers are curled around in this direction. So I know that around the bottom, the magnetic field is going to be going in this direction. Cool, all right. Now if we expand that out, this is what we were talking about before, expand that out to every single one of those wires, this is essentially what we'd end up with. What do you think's happening on the top of the solenoid, on the bottom of the solenoid, and in the middle? So remember, I've got magnetic field from this one, magnetic field from this one. There we go, magnetic field, and I'm just looking at the very, very top, very bottom, and of course, middle of that solenoid. Start to see a bit of a pattern there, right? It starts to show up. Essentially what we look at is those all summate or add up outside of the solenoid. So we end up with that stronger magnetic field outside of the solenoid. We end up with an even stronger one inside. So significantly stronger inside. And then if we were to connect these lines, because remember magnetic field lines are typically closed loops, if we were to connect them, we would see that it's actually starting to look a lot more like a magnetic field. So if I were to put a shape here, how the heck do I make a shape? There we go, I figured out how to make a shape. But if I were to replace that solenoid with this particular shape, all of a sudden those magnetic fields are really starting to look like a magnet, right? Or the ones that are around a magnet. So not thinking about the ones that are inside of the solenoid, thinking about the ones that are going around the outside, they're really starting to look exactly like our magnetic field for a bar magnet. So we would have our north side over here and our south side of the bar magnet over here. Remembering that the direction a compass would point is away from the north on this side and then towards the south on this side. So really, really, really starts to look like a bar magnet. That being said, know that this is first and foremost, it is not a bar magnet, it's a solenoid, and this is because of how the magnetic field is created in the middle of the solenoid and around the outside. Cool, so here's a quick question for you. What would happen if we put a soft iron core inside of the solenoid? And what we mean by soft is it's not like mushy. Soft is dealing with those domains. Right, so soft means the domains are easy to change around. What would happen to those domains? Well, at first they'd be scattered, but realistically, if they're in the presence of a magnetic field, they would align themselves with the magnetic field. So remember, each of these is a little tiny north and south, a little tiny magnet. Those domains are going to align themselves, so they're pointing in the direction of the magnetic field, which is going to create an even stronger magnetic field. And again, looking at this in terms of a bar magnet, so if I get a shape back here, let's get that shape in there. Looking at this in terms of a bar magnet, okay, bear with me here. Essentially inside of the black there, it looks like the domains inside of a bar magnet. It looks like we've got the north side, the south side, which means overall the north side of the magnet is, whoops, is over here. Overall the south side of the magnet is over here. And then the magnetic field looks exactly the same. Again, this is because we've got that magnetic field from the solenoid. So yeah, this is the idea of an electromagnet, right? And you might remember from grade 2 or something like that when you actually made electromagnets. This might be something you want to try out at home. All you really need to do is wrap, if you've got some wire, wrap up a nail over and over and over and over and over and over again in the same direction. Hook it up to a battery. So hook that wire up. The battery would typically look more like this. You can just connect the wires to one side and to the other side, and then you've got them wrapped around your nail. And then see if that's a horrible drawing. See if you can pick up some paper clips or something with that, right? I bet you can. So you're going to create your magnetic field. Now, one interesting application from this is MRI scanners, so magnetic resonance imaging scanners. So essentially what we see with this is you see this section right here is essentially just a gigantic coil of wires, like a huge, huge, huge coil of wires that creates a massive magnetic field. And then what happens when it creates that massive magnetic field and the person's in here, you have your protons that are all spinning around. So your protons are your hydrogens in your body that are all spinning around. They're all moving. They're all creating their own magnetic fields. And when we turn the magnetic field from the MRI on, they all essentially align themselves, hopefully you can see this okay, with that magnetic field. And then as they go back to their ground state, they release that extra energy that they have that they've taken into like flip, and then they give off radio signals, which can then be picked up by a machine and create images of what's inside your body, which is kind of cool. So anyways, if you want more info on that, check it out. There's loads on the internet of information about that. So this kind of leads us, like we just explained solenoids using hand rule number 1. This leads us to hand rule number 2. Now the shape of hand rule number 2 is exactly the same. So it's those curled fingers and it's your pointed thumb. It's just what they mean are a little bit different things. So for hand rule number 2, your curled fingers are the direction of the current around the solenoid. So they're essentially following the wires and which direction the electrons are flowing around those wires. And then your thumb points towards the north pole of the electromagnet. I even like to think about this before you start thinking about north or south, because that's what gets a little bit confusing for people. It's the magnetic field inside of the solenoid. So your thumb is the magnetic field inside of the solenoid, which then leads us to the north pole of the electromagnet. And once again, so this is actually never going to change. Whenever we're using negatives, we use our left hand. So here's the diagram or the picture that we've got over here for this. So the electrons are flowing up across the front of each of these wires. So I need my fingers going up across the front, and then the electrons are going into the page across the top. So I need my fingers going into the page across the top. That's a little messy. I need a skinnier felt pen. Into the page up top. So essentially they are curling around the exact same way as the wires curling around. And then my thumb, so my thumb is pointing in this direction, that will give me my magnetic field inside of the solenoid, or give me my north pole as I'm treating it as an electromagnet. Cool. So similar sort of idea. Remember, which way would a compass point on the inside? So if my thumb is pointing towards the north pole of the electromagnet, this is where people get confused. You'd think that the north pole would point the other direction. But if we treat it as the magnetic field, right? So it's the magnetic field inside of the solenoid. The compass points with the magnetic field. So if the magnetic field is this direction, the compass is also going to point in the same direction. So that's the place where people get a little bit confused for this. So just take a second. You don't have this one in your workbook, but see if you can pause the video, see if you can figure out the north and south poles of the electromagnet, and also we'll add to this the magnetic field inside, just so that we're clear on those 2 points. So put it on pause, see if you can figure this out. You remember these power sources, I hope, from the last unit, so negative and positive. Go ahead and do that now. All right, so I like to trace the negatives. So the negatives are coming out of the negative side, the electrons are coming out of the negative side. They're going around the back, and then they're going down the front in every single situation, right? So out of the page up top. So I need to line my hand up for this one to make sure that that's working out pretty well. All right, so I've got my left hand out. I am pretending that I am holding that solenoid. So like holding that solenoid in my hand, kind of like that, and you got the coil of wires that are all going this way. So my fingers are pointed down the front, because that's the direction the electrons are flowing. And then my thumb, get a different color there, my thumb is pointing this direction. My thumb points towards the north pole if I were treating this as an electromagnet. Therefore, the south pole must be in this direction. And if I wanted to draw some field lines, then I would have my field lines going through this way, because remember, that's the direction my thumb's pointing. They'd be going out, out, and around in that direction. So it got a little bit messy there, but long story short, you can always pause, you can always rewind. Your thumb is the direction of the north pole or the magnetic field in the middle, and your curled fingers are the direction of the electrons around the actual solenoid. Cool, so now you've got this example. This example is slightly different. Now the question is, which direction would the compass be pointing in those two particular places? So we're looking for the compass directly on top and directly to the side. So again, put your video on pause here. Let's figure this one out. Alrighty, so I've got my left hand out. I've got it shaped like number 2. I got to go through and I got to figure a couple things out. I know that electrons, that's not anything that writes. I know that electrons are going to be flowing I don't know why it's changing colors so much, but the electrons are flowing that way. Therefore, they're going around the back and they're going across the front in this direction for every single wire. So I need to line my hand up like that. So I get my hand, I line it up. So I'm pretending that the solenoid is through the middle here. So I'm going to sketch a little cruddy solenoid, and then I've got the wires coming down this way. So I'm holding it in my hand. And I've got my hand lined up properly. So I know that my thumb is pointing upwards. I know that this is going to be the north pole of my electromagnet. This is going to be the south pole. I know that the magnetic field through the center is going to be going like this. I'm not really too concerned about the magnetic field as the center. Now we're kind of treating this as a gigantic electromagnet. So the compass up top, we know that the compass, the north pole of the compass is going to want to point away from that north pole that we've got right there. So the compass should be pointing in this direction. And then off to the side, it's pointing away from the north, but towards the south. When we add up those two magnetic fields, it is just going to be straight down on our page like that. And I erase the whole thing. Straight down on the page like that. Perfect. Now the last thing, we didn't do this in the other piece, but the last thing we want to talk about is, well, how do I show my work? So left hand rule number 2 is what we're talking about here, where our fingers are the current or the electron flow around the solenoid, and then my thumb is equal to the north pole or my magnetic field inside of the solenoid. So remember, it's both of those two things. Nice. So that's pretty much it for the actual lesson for this one. I know it's a bit of a longer one. I do have one more thing. I'm going to keep talking. If you want to pause it here, or you want to go start some practice and start working on things, that's a-okay. But there's one other little piece that'll help explain something that we talked about from a previous lesson. That's just showing my work. So the application for this, and again, this is the part where you can tune out, but if you want to hang out and check this out with me, that's a-okay. The applications for this is Earth's magnetic field, and actually Earth's changing magnetic field. So we already talked about how Earth was essentially a gigantic magnet with the South Pole at our geographic North Pole and our North Pole at our geographic South Pole. So it's essentially like a big magnet that looks kind of like that. What makes that magnet is actually our outer core. So our outer core is made out of iron and nickel and other heavy metals, mostly iron and nickel, and it's melted and it creates these convection currents. So the convection currents are essentially taking that melted metal, and the convection currents are spinning them around in very particular directions. The spinning of that melted metal, the spinning of some of those ions, is what creates the magnetic field. And we typically have an overall magnetic field. So if you follow each of the magnetic fields, I'll do them in black. The magnetic field coming down through those ones, down and up, starts to look an awful lot more like we've got our north and south poles in those particular places. So the reason it's changing, right, and it's a changing magnetic field is realistic. It's a liquid and it's just kind of going through and doing its own thing in those convection currents, taking the easiest path. Scientists know that it's changing, one, because there's a little bit of deflection like we saw in the last slide. So between 1900 and 1996, we've seen it change a little bit, but over history, people have actually seen it flip, right? So our magnetic North Pole was not always our magnetic North Pole, and South Pole, same thing. The evidence that we have for this, and when it's in a flip, it's apparently pretty wild, is what scientists predict. So you got norths all over the place and souths all over the place. The evidence that we have for this is actually through geology, to be honest. So there's tectonic plates. We know that the Earth is made up of a whole bunch of different tectonic plates. They're moving around based on the convection currents in the mantle. And it's where they're diverging. So diverging means moving apart. That we actually see this. And it's typically in like seafloor spreading is what they're talking about. So this tectonic plate moves in this direction. This one moves in this direction, and so on and so on. So A is the earliest in time. then B is in the middle, and then C, the diagram C is the latest in time, but the seafloor is spreading. So what happens when the liquid magma comes up, essentially on the bottom of the seafloor, it becomes rock, like solid rock, very, very, very quickly. The liquid magma aligns its domains with Earth's magnetic field wherever it is. So in one particular point in time, all of the domains might be pointing in, I need a skinnier felt pen for this, all of the domains might be pointing in one particular direction. So the colored ones, the domains are all pointing here. If the Earth's magnetic field were to flip, then we'd see the domains aligned still with the Earth's magnetic field, just in the opposite direction. So all of the white or non-colored ones have the domains aligned the opposite direction. So again, this way, this way, this way, this way. This is our evidence for Earth flipping. We can actually get a gauge on how often this happens based on how quickly, and assuming that the Earth's been going through the same processes since the beginning, essentially, we get an idea of how often this actually happens. It's not very often, but often enough, I suppose. And we see the evidence in the seafloor. So that is really it for our lesson today. Again, I know it's a bit of a longer one. No math involved with the practice though, so make sure that you know and make sure that you can deal with hand rule number 1 and 2, hand rule number 1 for current carrying wires, hand rule number 2 for solenoids. So that is it for now. Talk to you again soon, Physics 30s.